Is it better?
Yeah, it's okay. Yeah.
Okay. So thank you again, Song, for the great introduction, and just thank you to the whole APAN community because they've been very supportive of the work which we've been trying to do here. We always get very good feedback, so it's always good for us to present to you guys and see if we're doing something worthwhile or not. So for the last 5, 6 years, I've been leading research in developing AI solutions that can make networks self-driving and smart. We started with wide area networks because we were working with ESNet, which is a DOE network. And now we've kind of extended that research into wireless and also quantum networks as well. So that's a lot of the work has grown into that. So Hecate is one of the tools which we started working on 1.5 years ago, which is supposed to use AI to do better traffic engineering for the challenges which we see in the science research networks. So let me see if this, yeah. So one of the issues, the challenges which we're trying to deal with is optimizing network resources as it is. So I come from a software engineering background, and when I talk to network engineers, usually asking them questions like, what happens if you run out of network resources, for example, or you run out of bandwidth? The usual answer is we just buy more. And network equipment can be very expensive. It can go up to millions, especially if you go for like Cisco switches, etc. So my concept has always been like, how can we get more out of the network resources we have? And in particular, science research networks, where we do science transfers, which can be these big files, which are coming from the Large Hadron Collider, or even these small streaming files, which are coming from edge devices that are connected to sensors that are continuously streaming data all the way up to an HPC facility so that it can be analyzed further. In both these kind of cases, it's a multi-objective optimization problem because not only are you making sure that the transfers happen in a correct way, you are guaranteeing the service to the users, which are the scientists, for all of these kind of science workflows they work. You guarantee that there will be no loss on their experiments when the data is being sent, especially if they're taking images of potential galaxies and they want to make sure that all the data has been transferred so that they can analyze it. And we also want to improve the overall network performance to work better within our facility. So currently, there's been more and more discussion on how energy, which is green energy, is being involved in this whole concept of running networks as well, because until now it was kind of like not looked at. But in the next few years, we're going to start looking at green energy and how we can save energy while running our network resources as well. So in this particular project, we looked at traffic engineering because we wanted to do these guaranteed network transfers, get more transfers, have less congestion points, and also provide better quality to our scientists. So we started with this problem statement, which actually grew into 4 different things. So our high performance throughput with low loss for huge time sensitive data transfers. So these are data transfers you want to finish like in the next 4 hours so that you can do something else after 4 hours. So we can have time deadline transfers. And then latency sensitive communications. For example, I'm doing a video streaming over here, and if it's lagging, then you can notice it. So this counts into those sensors that are connected to devices, and you want to have latency sensitive communications coming from them. So we have a lot of network tools where you can do bandwidth reservation. So there is Oscars, NSI, tools developed by ESNet, tools developed in the EU, and most of these are open source. And you guys are using some of your own bandwidth reservation tools. So these are actually very important for us the way we do transfers. But overall, we also want to reduce bad quality of service on the network. And this is what we can define as for that. So all of these together become a multi-objective optimization problem because it's not just one thing which we're trying to optimize. So we're trying to use traffic engineering to address a lot of these concerns. The way I'm calling it is because we're trying to use the maximum of the network resources that are there, we're trying to run the network hotter. So rather than buying more resources, we just want to squeeze in as many flows into it as possible, at the same time not compromising on our quality. So this is where Hecate kind of started, and it grew into a bigger challenge, and I'm going to talk about some of the challenges which we're working on now. Based off of AI, it does a lot of data-driven active learning through experience. So we started with deep reinforcement learning, where you basically have this environment which is represented by a maze, and this could be your network topology, for example. And then you read in the state of the network, you learn what policy there exists, and you can do an action, and based on that, you get a reward. So this is very simple agent, which is learning through experience, like what the best strategy was. And I explain this more in the next few slides. So Hecate started off with that idea, and we started building up on what kind of layers would exist in it. As you can see at the bottom, we're starting off with a wide area network. So you have all of these routers and links, but you could also go into Raspberry Pis and FPGAs, which are connected through internet or any links. And then on top of that, you need a software that can control these devices below. So those could be SDN solutions, traditional traffic engineering solutions, PCE, or segment routing, which is what we're trying to do next. And then based on that, on top, you have something which is telling those middle layers that this is what you should be doing. So the thing on the top has most of your intelligence in there. So you can have simulation engines over there where AI could try out different strategies, and based on the best strategy, it can push the best solution down, and the network can reconfigure itself based on that. You can have optimization being done above again, and then pushing things down. We added this box called traffic class identifier because what it can do is that it could give different rules for elephant flows versus mice flows. So if it can recognize that there are 70% mice flows, which are streaming data on this particular link, I can optimize the link just for streaming data, and I reduce the performance for elephant flows, for example. And then all of this kind of hooks in with real-time monitors, which are deployed on edge systems. So you can have very simple APIs or very simple agents that are deployed wherever you can get real-time information. And this information is what is fed into this brain of Hecate, which can then push the actions down to the network configuration. Now, in theory, all of this works. We have a lot of issues getting this working in practical, which I'm going to show issues next. So our brain in the agent is actually taking in this information, which is network health data, which is real-time loss, real-time bandwidth, etc., all across the network. It also reads in the topology, and it also reads in what kind of elephant flows or mice flows currently exist on the network. And then based on that, it learns to either optimize for the average utilization over the network or just improve the latency across all the links. And you can add more rewards, like based on what you want to do with your science research network. So this is what we started with, that we're just basically going to optimize these 2 or 3 things. And this is the information available, and we're going to let the agent learn and perform. So this is just a bit more on the back-end stuff where some of the real-time data which is coming in, we have NetFlow deployed, which is bringing in flow records. That we use to do unsupervised cluster analysis to give us what kind of elephant, like what is the percentage of elephant flows or mice flows that exists. So you can write separate unsupervised classification algorithms that basically just read in the net flow record coming in, and it basically just puts it into buckets. And then you can take a percentage of how much the bucket is full with bigger flows or small flows. The other data which we're reading in is persona data, which is very simple to deploy, and it basically gives us throughput, utilization, it gives us loss, latency, all real-time data. And then we bring in graph neural networks because we do prediction on what the future is going to look like. So we read in for now at time t is equal to t. We run a set of graph neural networks right after that. And that gives us what t+1 or t+2 is going to look like in the future. Now, with both of these sets of data, and maybe you can add more data sets, we then push that into an optimizer, which can run through that simulation engine we talked about. And then that could help you orchestrate whatever the network good configuration should look like. And then when Hecate has this, it can push it to a path computation engine, which can reconfigure the routers to do what Hecate thinks it should be doing. So the graph neural network actually was one of the easiest thing to do because we found a lot of information online on how to write good graph neural networks, which can help improve the prediction accuracy. So the network is represented as red dots. So this is just nodes. And the rectangle over the green rectangles are basically all the values of the edge, which is loss, latency, throughput. So all of this is written as a graph, and then that's fed into the graph neural network. And then it produces t+1, t+2, t+3, whatever. And the more you predict, the error rate is higher. But it's actually better than using other kinds of time prediction algorithms like LSTMs or other time series algorithms, which we found. So you can build this stack of spatiotemporal data sets, and you can use this in your optimization techniques. So overall, this is what Hecate does. It reads in this, if you can see my arrow, it reads in this network data from the topology, network health, traffic patterns. It reads in these node and edge features, uses this as a graph representation, and then it runs a graph neural network to do prediction across the links, what the future of the network it thinks it's going to look like. And then it runs the optimization approach where it comes up with one solution, and that one solution is then pushed down to the routing, the routing update for the network to do things. Now, this particular case, you can either do a very greedy approach and do just a simple optimization, whichever optimization algorithm you want to use, or you could do another deep reinforcement learning approach here. But what we found is it just added more complexity because that would mean that you again wait for the DRL agent to learn what the best strategy would be at this stage. So it's actually better for us just to write our own optimization algorithm and just use whatever the machine learning has learned, like predictions, and then just do its own optimization and then push the commands down. Because you don't want to wait too long for Hecate to react. So we also want to reduce the time it takes to react and learn and push commands onto the network. So some of the issues which I found, in just a basic sequence of actions, you observe, collect data, you run the machine learning, and then you push the commands to the network. And we're hiding away a lot of the complexity in these three boxes. The biggest issue I found was actually pushing the commands to the network because not a lot of network devices exist that can take these AI commands and reconfigure the network very quickly. So I'll show you why. Traditional approaches look at SDNs, and those are what we were looking at. So you have a controller that is connecting all of these devices below, and you can compute routing tables, which can tell the agents or the flows coming in that which direction you should go. Firstly, it's not very easy to reconfigure routing tables, what I found the hard way. It creates a lot of delays. So there are not very easy APIs in which you can just push simple table updates. And it's centralized. This solution will fail as our network grows. So we need to find solutions where we can have like decentralized approaches where it doesn't matter how big our network scales. So what we started doing now is we've started looking at source routing, where Hecate can learn and build a label path, which can be pushed into the packet header. And then that allows the flows to go through the network. And this is what we're doing next. So what source routing is, so this is what we're doing is we're actually partnering with other people. So there is a group in Brazil which have this tool called Polka, which has published a few papers on how they've done successful segment routing. And this is an image I got from Packet Pushers, where basically what happens is when when a flow arrives, it comes in with a possible set of labels that I'm going to go 16006, 16004, for example. And what it does is it just comes in, it looks at what the label is. Based on that, it says, okay, you're going left or right. When it reaches the next step, it pops the first label, and then it sees what the next label is. So those popping mechanisms actually guide the flow to go through the network. So you can see that there is no centralized control over here, but it's just a big update where we just have to push stuff down and the flows will have this information. So Polka has successfully done this. They've demonstrated it on various networks, small SDN kind of networks. So what Hecate's team or us are doing right now is we're collaborating with Polka on just this part to help us do the pushing of the AI commands. So this is called packet forwarding, where the controller or Hecate will calculate the route, and this is saved as a collection of port numbers. And these could be egress port numbers as well, because each router can have multiple egresses. And then that basically guides the flow, go left or right or another possibility as it goes through the network. Some of the issues, again, we found here is that we still don't know if P4 supports this. So if P4 actually supports this, it's going to make a lot of our life easy, because it's also one of the favorite tools right now in industry and universities. So we are exploring this, and we're hiring a student to help us explore P4 to support this label forwarding behavior. There is also lack of hardware support. Not a lot of switches actually or routers allow segment routing right now. So I think there's also an IPv4 and IPv6 issue, but we're currently exploring Palo Alto switches to see if this can work on a small network setup and see what we can do. So here we're using the experience of Polka's team actually to help us learn from this, from what they've learned. There's a lot of information. They've demoed their version in SC 2023. They've won many awards, and they've also deployed it using P4. So we're partnering with them to learn this thing. So if people are interested, I can send more information. This is work which is currently happening. We're setting a test setup in the SDN lab at Caltech, where we have this kind of a setup, and you can simulate different kinds of flow and see how the segment routing piece would work. So some of the problems we're exploring is if we have flows with varying sizes coming in and with varying priorities or deadlines, how can Hecate push the correct flows to go through? So we don't have results yet because we're still exploring this idea, but I think segment routing is the answer for us, and we've started getting some simulation results. But again, out of scope of this whole thing is we are not exploring TCP congestion control, because there is another issue that you can optimize your flows based on congestion control. That is out of scope. We're also out of scoping the buffer sizes and their specifications of which algorithm they are using, because we are only focused on decentralizing the routing decisions that are coming and as the networks scale up. Some of our simulations are done in 10 gig and 25 gig. We're hoping to do these experiments at 100 gig speeds, which is possible through the Fabric testbed that is now available for everybody to use. And this is just a map of what kind of topology we're building on Fabric. Yeah, so we're exploring this new direction with Hecate. We'll love to hear any feedback. That's my email address. We're hiring a postdoc to help us with this project, and also students. So if people in the room are interested, feel free to reach out to me. And any questions?
Any question? I have two
I have a
questions.
question.
The first one is what kind of metric are collected from the NetFlow and Persona? And you have used two tools for the collecting the metrics. And can you explain the metrics for the each collectors?
Okay, so NetFlow collects NetFlow collects our simple flow records, which are source, destination, file size, and also TCP versus UDP, and the time at which the flow came. So it's just a simple 5-tuple thing which comes in. So we are using that just to understand what is the distribution of big files versus small files on our network. So the flow, is it a big file being transferred or a small file transfer? So that's NetFlow records which we're collecting. Then perf so NetFlow comes in every 5 minutes, and we filter to remove repeated flows for getting this information. And then Persona comes in every 30 seconds. So that's a time series data set which records latency, loss, and throughput. So that's recorded across all links wherever Persona is deployed. So that's just a time series thing which we use.
And most of our metric for the AI machine is from the Persona, right?
Yeah, most of it is from Persona. And we've heard about S-Flow as well. So S-Flow is another team which has approached us that we should be using their things because they have better data. We haven't yet explored it, but people have approached us that you should be using S-Flow as well.
Also, you mentioned the source routing would be better than the SDN approach. Then do we have any performance comparison data between the segment routing and you have used the segment routing for the source routing, right? Then do you have any performance or comparison for that?
No, we're still testing this out. So no performance data, but yeah, we're just thinking about scaling. That we don't think SDN would be able to scale, but that's a good point that we can think of performance data comparisons. So
Okay, thank you. Then
I have a question.
sure,
Can I ask?
sure. Oh,
So just curious about the identification of the file size for the large flows. So one of the challenges obviously is that the network has no awareness of how large a flow might be simply because it doesn't know the file size. And so I'm curious how you're approaching that aspect of it.
okay. So what we've done is we've written a classification algorithm, which is an unsupervised classification algorithm. So a NetFlow record, when it comes in, it has source, destination, and file size in it. So it does have like whether it's a 1 gig file or just 200 meg file. So that information is in a NetFlow record. So keeping that aside, what we've done is that we designed a classification algorithm, which is like very simple k-means approach, where we took for a month's data, a NetFlow month's data, and we trained it to understand two major clusters. And the two major clusters are basically divided based on sizes. So once the algorithm is trained, it knows two clusters have these certain characteristics. So then when a NetFlow record comes in, it matches it into this classification. It groups it either it's closer to this cluster versus this cluster. And that helps us label the incoming flow as whether it's an elephant flow or a mice flow. So that's our approach behind the scenes. Does
Okay.
that answer your question?
Okay, then is there any question from remote side?
Yes, Professor, I have.
Okay, you can ask.
Thank you, Dr. Mariam, for the great presentation. The first question is like in slide number 7, you mentioned about the DRL agent. So I want to ask that which specific DRL agent you are using for this architecture? Architecture.
Yeah. Yeah, we did a simple DQN approach over here.
Mm-hmm.
So it's a simple deep queue network, which we are developing for this. And we also tested multi-agent approaches here. So we had multiple DQNs deployed. So that's a DQN is very simple because you can define the state as the network stuff. And the queue becomes what you are learning, the policy. And the action is whether you're going left, right, or whatever other paths are possible through that particular router. So it's a centralized approach. So when it comes to node A, it knows like how many paths I can go out of. So it learns those actions, and then the next node and whatever actions are possible.
I think here is your states quite big. Like for example, you are taking network health data and topology and traffic classification.
Yeah.
Yeah. So I think is it possible, like for example, DQN? For example, in DQN, many researchers facing a lot of problems. For example, when DQN interacts with the states, it makes a queue table, right?
Yes.
So there's a problem like it consumes a lot of memory. So how you tackle this challenge in your research?
So DQN is supposed to help with that memory challenge because it builds a neural network to represent that table which you said it learns. So
Yeah.
rather than having a linear table, so the neural network will learn that. So DQN approach actually should help with that. But there is another approach called DDPG, which allows you to learn more states and more actions. So that is another favorite of ours that we sometimes use as well.
So I think in your case, like DDBG is best for example, because it's continuous space. So I think I suggest that you can see for the DDBG algorithm because it interacts with the continuous space and then it learns whatever data you have. So I think DKN is not best suitable for this case for your architecture.
Yeah. Okay. Yeah, that's a good suggestion.
Yeah. Thank you.
Okay, thank you. Thank you for your presentation, Mariam. I appreciate your continuous contribution to our session. Thank you. Thank you very much.
Thank you.
Okay, then we can go to the second speaker. The second speaker is Kohei Ichikawa is there from the remote side.
Yes, yeah, from the remote.
Okay, then
So let me share the screen.
the Dr. Kohei Ichikawa is from the Nara Institute of Science and Technology from Japan. His the presentation title is Empirical Dynamic Modeling and Cybersecurity Inspired by Brain Neural Network Analysis. Thank you for your presentation. Then you can start, please.
Yeah, thank you for introducing me. So also thank you for having me here. So I'm really appreciate to invite me to here and giving a talk. So my presentation is empirical dynamic modeling in cybersecurity inspired by the brain neural network analysis. So this is collaborative work with international team from the Japanese team and then also from the United States. And then he is recently moved from the US to Japan in currently working on the Okinawa Institute of Science and Technology in Japan. Anyway, so let me get started. Okay. So this is the overview of our study. So our study aimed to build an accurate machine learning model to detect network attacks like DDoS attack. This model is basically inputs the time series of data of network metrics and then predict the network future network state with some prediction model. And then we get the actual observed metrics and then also the time series predicted data. And then using the both observed data and predicted result, we put those data to some classification model to detect this observation is abnormal state or still normal state. So this is a overview of our study. And then here for the prediction model, we are going to apply empirical dynamic modeling called EDM to make an accurate prediction for this study. So this is the overview of our study. And then first of all, so look at this time series data. So can you imagine, so what kind of the dynamics or patterns might be underlying this data? So I think so it's pretty hard to find meaningful patterns from just like this random like time series data, right? So, but this is actually from the very simple and typical model called Lorentz attractor. I think many of you seen this kind of the model. It is called the Lorentz attractor system. So if we look at the true model like this, it looks very simple, but the actual observed data like this is very hard to understand. So this is happens in many cases, right? And then and then the problem is we don't even know the true dimensions of this model. So for here, for the simplicity, so I just give you just a 3 dimensions model here. But in the actual case, in the real world problem, so we don't even know the true dimensions of the models, right? So that is a very quite difficult to understand the true model from the data, right? So, but here is a very useful techniques called the Tarkin's embedding theorem. This is a technique to reconstruct the attractor model like this from the observed data. Okay, so the technique is actually very simple. So first of all, so we have just one single observed data, and then we prepare the shifted data like this in this case. So we have the original data, and then this one is just shifted data by tau, maybe tau second or something. And then we have another data shifted by 2 tau here, right? And using those just lagged time series data, we can draw this kind of the model. So and then you can find that this is a very looks similar to the original model, right? So the important thing is that we can remodel this kind of the similar model using just one single observation with the lagged time series data. So this is very simple, right? And this is actually the very powerful analysis techniques developed by Tarkins. And then, so even if we don't know the true dimension of the model, so we can make any number of dimensions using the shifted time series data. And then after that, so we can make a prediction model like that find the neighborhood data, nearest data from the past data, and then find the future data based on the past data. So for example, if we want to have the t times after data, so we first need to find the nearest data from the past time series, and then find the t times after data from that past data, and then average them to predict the future data using the past model, past time series data. So this is the basic idea of making a prediction model using the Taken's embedded theorem. So the EDM is actually the technique used this Taken's theorem and then make a prediction model. And then as the name suggested, so the empirical modeling EDM is based on the data. So it tries to make a model based on the observed data only. So that's why it has empirical in the name. So originally, so we have been working on using this EDM to analyze brain neural activities. So in this study, we observed the whole brain neuron activity in the small fish, and then try to find the causal relationship between the neural activities. And then in this research, so we have actually making this KEDN. It's a very high performance implementation of EDM. I think this is still the world's fastest implementation of EDM for now. So if you are interested, so let's take a look at the information for detail. So, but anyway, our goal of this study is try to use this EDM to detect network attacks. So because the network metrics is also something like the time series data like this. So we may you may be able to apply the EDM to predict the time series data, and then maybe we can also detect the DDoS attacks in the observed event, right? And then this is a more detailed approach of our study. So first of all, so we make a prediction model based on the observed time series data, and then make a predicted steady state here. And then using the both observed data and then predicted data, we make some classifier to detect which part is attacks, which part is normal. So this is the goal of our research. And then here is the other models to predict the network states. So for compression. So the first one, so auto-regression is a simple regression model to predict the future value based on its past value. It's basically the regression model based on the past value. And then the second one is long short-term memory. So I think this is also very famous deep learning-based model to predict the time series data, right? And then comparing these two models with our EDM-based model. So I think we currently expecting that EDM can predict the higher accuracy than the AR. So because the auto-regression is a very simple model. So I think the EDM should have higher accuracy than the AR. But for LSTM, I think LSTM is more sophisticated technique, so it should have more higher accuracy. But the EDM should have shorter runtime compared to the LSTM. And this is the data set we are using. So it's DARPA Scalable Network Monitoring data set. This is a synthesized data set created to simulate a real internet traffic and network attacks. It contains basically a synthetic background data and then contains the large-scale network attacks, including the DNS worms and then DDoS attacks. And then here is the process of training our model. So first we split the data into two parts, and then we make a model based on the first half of the data set, and then make a model, and then evaluate this model with the last half of the model, the last half of the data set. So this is just a training. So in the training process, so we are trying to find the optimal number of shifted time series data. So EDM need to make a shifted time series data, right? So in the process of the training, so we will identify what is the optimal number of shifted time series data. So that means that how far back so we should need to see the data in the past, right? So the shifted data basically look at the past data, right? So that identifying the optimal shifted value means that identify how much far we need to back to see the data. And then AR and LSTM also need to find how much past data need to be fed, right? So it's basically similar to optimize the model among those three models. And then this is the actual prediction result. So this is the example of the count of the sync racks. So this is time steps, and then the vertical axis is the number of count of the sync racks, and then this is the purple line, the observation, and then the other colors are result from the those three models. And it looks like the very similar among those. So, but here we are looking at the RMSE, so it is error value of the prediction. So in the horizontal axis here is the number of embedded dimensions. So this means how much second we see back in the data. So here, so the purple line is the result of the EDM. So if we look at the maybe 10 or 20 seconds, that the EDM result is better than the other model. And then AR is very steady, and then LSTM has some fluctuation like this. So anyway, so here now we have the two data. So observed time series data and then predicted metrics here. And then using both results, we can make a classification model. So to predict that, to identify that this event is the attacks or not normal. So here we use the random forest classifier to make this classification model. And then actually, so to make this model, so we even make a model only on the observed metrics without predicted metrics, like we make this metrics by EDM or AR or LSTM in this time, but the classification model itself can also make this kind of model using only on the observed metrics. So we'd like to compare among them. So here is the actual classification performance. So here the first line is the model just based on the observed metrics only without predicted model. So that one is still high accuracy, but it has a low F1 score. So F1 score is kind of the matrix balance between the precision and recall. So if the low F1 score means that the result still includes the many negative, false positive and false negative values. So but here in EDM and AR and LSTM, so as we expected, so LSTM has the highest accuracy right here. And then EDM is actually the second accuracy. It's still higher than the AR model, right? So this is as we expected. And then this is the runtime of the prediction. So AR is very simple model, so it's just here, right? This, so it's super fast compared to the other model. And EDM is still fine. So even if we have the large embedded value, the runtime is still practical. But the LSTM is increased linearly if we increase the number of embedded value, right? So this is the conclusion. So we found that modeling the behavior of the network using the observed network metrics, and then it's improved by the EDM, and then EDM is less expensive to run than deep learning model like LSTM, but it shows still satisfactory performance. And the future work, so we will try to apply more capability of EDM. So actually, so today, so I just introduced the one of the function of EDM, predict the future value with a single time series data, but the EDM has other function like the convergent cross mapping is detect the causal relationship between the multiple values. So this is the future work for us. Okay, so that's it.
Okay, thank you. And is there any question? I have a question. You have used Lorenzo attractor and Taken embedding theorem. Can you explain your motivation for choosing those Lorenzo attractor and Taken embedding theorem? I just want to know the special or general features of the attractor and embedding theorem.
So the observed time series data from the network is also like this kind of the time series data. So we think that there is some mechanism to make this kind of the time series data on the network metrics too. So that's why we want to have some Lorentz attractor system. We think there is some Lorentz attractor system behind the network behavior. So that's why we want to make this kind of the model behind the network. Is it okay?
For the Taken embedding theorem, is there any feature for it? Treating it?
So sorry again.
Then you have used also the Taken embedding theorem. Then is there any the special feature of the Taken embedding theorem?
Oh yeah, so the Taken's theorem is very, so actually it's very useful method to extract the attractor system from data. So if we look at the true model and then the true dimension of data that directly observed from the model, so it is maybe ideal situation. We know the true model and then true data, but in in realistic problem in our actual work. Well, so we don't even know the number of dimensions to explain the true model, right? So that is a problem. So when we model the actual model in the Lorentz attractor, so the Tarkin's embedding theorem is just find the optimal dimensions. So using the just lagged time series data. So when we analyze the accuracy using the lagged time data, and we can find the optimal number of time series data, and then that is the optimal number of dimensions to explain the model, right? So the Tarkin's technique is useful to identify what is the optimal number to describe the actual model based on the data only. That is a useful function of Tarkin's.
I have also developed the anomaly detection system on Korea Research Network. And but your presentation is just for the DDoS attack. And can you apply this your mechanism to the anomaly detection for the general anomalies?
Yeah, I think so. Yeah, I think that is could be also future work for our research. Yeah, thank you.
Thank you. Is there any further question? Thank you for your presentation. Thank you.
Yeah, thank you very much.
Then we can go to the further presentations. I'm sorry. The third speaker is Yun Long Lu from Beijing Jiaotong University. I'm sorry, I cannot search my file.
Okay.
His presentation title is Digital Twin Edge Networks for Intelligent Transportation. Thank you for your presentation. Okay, thank you. You can start now.
Okay. Okay, thank you for your introduction. And hi everyone, I'm Yulong Lu from Beijing Jiaotong University. And it's my great honor to be here today to share some of our recent work on digital twin networks. And I will start my talk from the following four aspects. First, I will introduce the visions and the challenges of our future intelligent transportation. And then I will give the definition of digital twin edge networks. And thirdly, I will present the key issues in detail for intelligent transportation. And then finally, the conclusion and future development will be discussed. So first, let's see the visions and the challenges of intelligent transportation. So several worldwide groups have launched a series of research projects regarding 6G empowered transportation. For example, European Railway Research Advisory Committee has issued the Rail Routes 2050, while the 6 Genius Research Program of Finland designed the 6G network and the technology with autonomous driving as one of the main application scenarios to support actual high reliability and with the 1 millisecond latency and ultra high speed mobility. So 6D enabled intelligent transportation is envisioned to be ultra low latency and fully connected ubiquitous intelligence. And in terms of latency, the peak speed of 6G will be 1 TB per second, and which is more than 50 times faster than 5G. And the connection density of 6G will be 10 million connections per square kilometer. Numerous IoT devices will be fully connected. Moreover, the edge intelligence will be realized from MEC servers to the end devices, and the new distributed AI algorithms such as federated learning will be also implemented for ubiquitous intelligence. So the new characteristics of 6G-enabled intelligent transportation will be real-time autonomous operation and intelligent decision-making at edge, and enhance the connectivity and the security to realize these features. The new techniques such as federated learning and blockchain will be employed to achieve real-time perception, vehicle to roadside coordination, and ubiquitous interconnected intelligence. The digital twin will also be leveraged to improve the network efficiency and reliability. So new challenges also have been raised. First is massive connections, including IoT devices, sensors, and vehicles. Second is the trusted and secure interactions. Vehicles and smart devices in IoT generate a huge amount of sensitive data. The security and the privacy of this data need to be protected. Thirdly, services such as autonomous driving and navigation requires ultra-low system latency to guarantee the service quality. Fourthly, emerging applications such as 4K video service and VR also require a huge amount of resources. So these challenges need to be addressed to improve the running efficiency and the service quality of future ITS systems. So to tackle these challenges, we can employ various emerging enabled technologies. So next, I will provide a brief overview of their concepts and principles. So firstly, the digital twin. Digital twin is the key enabled technology for 6G. They are the digital replicas of physical objects, such as devices, systems, or physical entities. With digital twin, we can map physical objects to digital systems and keep the real-time synchronization between physical world and digital space. So DT can improve the performance of physical systems and reduce the maintenance cost while increase the system reliability. And in addition, digital twin can allow our operations only fail in the digital space, so can reduce the failure risks. The typical working mechanism of digital twin is shown in this figure, and physical systems transmit real-time data and update their status to digital twins, while the digital twins then will analyze this collected data and train models and update the digital twin models. Based on the updated models, digital twin can optimize the running of physical system. Another one is the distributed AI and such as federated learning, and among them, federated learning has been widely investigated and achieved a great success in recent years. The devices that participate in federated learning only transmit the parameters instead of original data to the server, thus can protect data privacy. The devices train local models through gradient descent algorithms, and while the server will collect the local models and aggregate them to a global model. So the local training process is to find the optimal parameters to minimize the loss function, and while the global model aggregation aims at minimizing the global loss function. We usually use methods such as averaging aggregation, as illustrated by the following equation to aggregate the parameters. So here is an example of using federated learning for traffic prediction. And in traditional scenarios, we share the large amount of video collected by the monitoring cameras and use centralized AI to predict the traffic states. While we use federated learning, smart cameras train their local models and transmit models to the target servers to predict its local traffic states. So in this way, the transmission overhead will be significantly reduced and the data privacy will be enhanced. Another technique is that can be used is transfer learning, and the goal of transfer learning is learn to learn and transfer knowledge from source domains to the new target domains. The research issues include what to transfer and how to transfer and when to transfer. So this is the transfer learning. And in the second part, I will give the architecture and the model of our proposed digital twin edge networks, also can be referred as DTN. So the architecture of DTN is shown in the right figure, and there are 3 layers, including the physical entity layer, and the edge layer, and the digital twin network layer. The physical entities execute local computing and transmit the results to the edge layer, while the edge layer perform real-time modeling and updating. And in the DT network layer, DTs connect to each other and share network resources. So here is an DT example case of autonomous driving. And in the access layer, vehicles connected to the digital twin layer through V2X connections. And the digital twins collects and analyze the environmental data and make optimal driving decisions. So this is a bi-directional process where physical vehicle data is used for building DTs, and the DTs will in turn optimize the driving decisions. This figure shows the vertical view of DTN architecture, including physical layer, full device DT layer, and the DT computing layer, service DT layer, and the application layer. So the benefits of digital twin include real-time computing and modeling, and reliable wireless communication connection, and optimize the simulation decision making. While there are also several challenges, including maintaining digital twin requires a lot of resources, and the heterogeneous ability of devices, and the limited wireless bandwidth resources. So these are all the challenges for building the DTN system. And in the third part, I will present some of our efforts in addressing the key issues of employing DTN in intelligent transportation. So the challenges of DTN primarily includes the following aspects. First is the modeling approach. DT requires the utilization of high-security and AI algorithms to characterize the features of physical entities. And the second is the computational and the communication efficiency of digital twins. Handling a substantial volume of data for processing and transmission is necessary, yet system resources are also limited. So in addition, the security and privacy of DT data need to be ensured, and the established DT model should be reliable. Moreover, real-time continuous synchronization and updates between DT models and the physical entities are also necessary. So these are all the challenges for building the DTN system. Regarding these challenges, we propose to use federated learning to build DTN. So why we adopt federated learning? There are mainly 3 reasons. First is data distribution. Large amounts of source data are generated in distributed IoT devices, and the data is also highly distributed. And the second is efficiency. Federated learning reduces communication and centralized computing loads by transmitting model parameters. In addition, privacy of the original data can be preserved by sharing model parameters instead of sharing raw data. So the rules of federated learning includes building DT models from historical data and updating DT models through iterative processes and analyzing and optimizing the constructed DT models. So a simple DT model can be represented as follows, where D represents the raw data and S denotes the operational state. The object objective of DT construction is to train a model M to minimize the global loss function. And we employ for the learning to train this model. And clients and servers represent end users and base stations. So in summary, when constructing DT in the IoT networks, there is a need to synchronize a large volume of data. While communication and computing resources are limited, and there is also the risk of data privacy leakage. So we use federated learning to build digital twins. And however, there also exist some challenges. One of them is the communication efficiency. With the development of AI and neural network technologies, model parameters are becoming increasingly large. So while in federated learning, it requires frequent parameter exchanges and posing significant challenge to communication efficiency. So furthermore, the synchronous communication mechanism of federated learning also lead to the efficiency shortcomings. For example, in this figure, user 2 is slow in computation and communication, and so we need to mitigate the performance imbalance between the users. Some possible solutions we have been considered, for example, such as user selection, and we maybe select the better users with the better performance. And another is resource allocation. For example, allocating more resources to user 2 while reducing the resources allocated to user 1 and user 3 to improve the overall efficiency. So like indicated in the figure. In summary, the traditional federated learning introduced significant waiting delays due to the presence of slow nodes. Therefore, we propose a asynchronous federated learning mechanism for building digital twin. Asynchronous federated learning involves selecting a subset of users to participate in the global aggregation process, while the remaining users continue with the local training. So we initially proposed using reinforcement learning algorithms such as DDPG to optimize the selection of participating nodes. Nodes that are not chosen for global aggregation will continue their local training and will maybe participate in the global training in the next round. So like shown in the figure. Another issue that federation face in detail is the question of reliability. It includes concerns about the privacy of model parameters and the reliability of model the models. So in detail, we propose to integrate blockchain as a connecting item to enhance system reliability. In this setup, for the learning conducts local training at the user level and transfers model parameters, while blockchain will collect these model parameters and store them as the transactions. It also verifies the aggregated global model through consensus protocols. The consensus process for model parameters involves first we'll aggregate parameters from device by the BS, and next the system selects validation nodes, and finally the model parameters are verified through the consensus process. By embedding blockchain, the states and the models of DT are stored in the blockchain, and the reliability of model parameters will be also ensured through the validation of blockchain nodes. So blockchain has established a reliable collaborative mechanism among distributed participants, enhancing the security and the reliability of digital twins. However, the introduction of blockchain can also slow down the overall efficiency. For example, in further learning and the consensus process, slow users may lead to communication bottlenecks and lead to the longer waiting delays. A slow user may be due to the difficulties in timely completing parameter transmission caused by limitations in communication resources or caused by the bad channel status. So in this process, in iterations, in the second iteration and the third step, the traditional mechanism requires waiting for model M2 to be confirmed by consensus process, which will result in significant delays. So therefore, in the second iteration, we don't use M2, but instead we'll use the confirmed latest model M1 as the global model and send it to the end users for local training. So to improve the consensus process, the efficiency of the consensus process. The last example case is about how to achieve low latency in DTON. We studied the edge association problem in DTON. So we defined the unique edge association problem in DTON. That is to map the physical users to the correct digital twins in edge servers. So as shown in this figure, we also give the mathematical definition in the equation. And the DT is connected to a DT network in the digital space. And the edge association problem is to place DTs in the digital space and then connect physical entities with the digital twin nodes. We propose the multi-agent deep reinforcement learning algorithm to find the optimal edge association strategy. And the multiple agents share the system states and collaborated with others to make joint association decisions. So the proposed edge association method has achieved good performance, including improved optimization, convergence, and the reduced latency. So finally, in the future, the convergence of federated intelligence and blockchain for building digital twin networks can be further investigated. And the proposed DTON can also be used for remote online coordination, including smart manufacturing and remote control. DTON can also be used in intelligent inspection, for example, to inspect the ROV status and monitor the transmission lines of the smart grid. Also, DTON can play an important role in the development of future metaverse space. So this is the end of my presentation. Thank you for your attention.
Thank you for your presentation. Any question?
All right. Thank you for your interesting presentation.
Thank you.
Like you mentioned that in ITS we need very low latency, and
Yeah.
It seems like you put your replica, your DT digital twin network to be placed between physical entity and the core layer, right?
Mm-hmm.
And
yeah,
would this may generate additional cost to slow down the latency or the traffic flow that can be problematic. For example, actually for safety reason like accident warning messages. Yeah.
Okay. Thank you. And the latency while we introducing digital twin into the system is a major research issue that should be considered. And I think it will introduce additional costs, but we have also investigated how to mitigate the effect. For example, we can simplify the model of digital twins. It means not the full replica of physical systems, but only we only mirror the message that we needed to construct the digital twin. For example, in the accident warning, we may only need to transfer little data related to the like obstacles in the railway to build a simplified digital twin model to improve the latency performance. Yeah, I think that's the solution we adopted at present.
Yeah, in another aspect, that would be something like we need to consider like security reasons, because like
Yeah.
when we put something like PKI or the computation power or something like that can be another factor that need to be considered, I think. Thank you
Yes.
for your
Yeah.
interesting answer.
Yeah, I think so.
Thank you.
The privacy should be carefully considered also. Yeah.
I think your presentation is very interesting because it is it could be the pre-stage for the Metaverse Zero, and I also have just one question. Actually, the client devices could be very varying. So some devices are very high-end devices, and some devices are
Yes,
very
sir.
low.
Sorry, my network just lost now. Could you pardon your question?
Yeah, actually, thank you for your interesting presentation.
Yeah, thank you.
Yeah, it would be very interesting because it is related to the pre-stage for the Metaverse Zero. Then you have used federal learning mechanism, but the client devices could be very different. Then some devices are high-end devices, and some devices are very low-end devices. And I think the difference from each devices due to the performance difference could be so large. Then actually you have used asynchronous federation learning, but what kind of the result from what kind of result from the each devices are required for your system? Can you explain any example result from the federated learning from each devices?
So you mean why we need to adopt the federated learning?
Yeah, actually, the federated learning is for the each client devices, right?
Yes.
Then I'm just curious about what kind of data from each client device can be required.
Okay. Yeah. I think so. So thank you. And I think the what data we should be transmitted to the server, it may depends on the application scenario or the service we want to use. For example, in the traffic prediction, the scenario, we may use the traffic data, like the number of vehicles and the timeline and the route locations to train the federated learning model, and the model will be decide which way is the better way to go during at present or at what time to guide the driver to select a better way with the less time. So I think the data we should use to train the federated learning model is highly depends on the service or the application we want to use federated learning. So I think so.
Thank you. Thank you very much. Thank you for your presentation.
Thank you.
Okay. Thank you.
Okay. Thank you. Thank you, Aaron.
Is there only one speaker is remain? The last speaker is from my university. He's my student. Amar will explain our project. We have started a new project for the satellite network, and we will explain our project briefly. Yeah, thank you. Amar.
Thank you so much, Professor. Hello, everyone. Good morning. It's okay. So, my name is Amar, and I'm going to present this IBN at Sargent, the outlining the satellite networks blueprint for Jeju NGN ecosystem. So we have a project of this Sargent network. We are actually making a satellite launch pad in Jeju Island. So on base of that, we are proposing a network architecture which will be based on the IBN. So my presentation is all about this IBN at Sargent. I will be highlighting what is the Sargent network and why we actually require the Sargent network, and also I will be then explaining about the intent-based networking, a little briefly explaining about the intent-based networking. Then I will be providing that how our intent-based networking will be integrated in the Sargent network. And then at the last, I will be highlighting some special cases of Jeju Island. So starting from the very basic, that we have the cellular network. These are actually, I will be going very quickly through this because we have already like run out of time. So yes, I'm going to short this stuff. So these are just the evolution, how cellular network evolved from 1G to 5G, and currently they are moving towards like thinking about to move towards the 6G networks. Like in 5G, we have the EMBB, enhanced mobile broadband, and mobile massive machine-to-machine type communication, and ultra reliable low latency. So for moving out to the 6G, they are having a plus like an enhanced version of the enhanced mobile broadband network, and ultra reliable low latency plus, and more massive machine type communication plus. Also, they have added two more things like integrating the AI in the network, and also the sensing like industrial automation and something like this. So for going towards the 6G, these are some comparison table based on in 5G. In theoretical, they were about to get like 1 millisecond of latency, but in 6G they are like trying to achieve like it is in theory, but yes, they are trying to achieve like 0.1 millisecond of latency. Also, the coverage area is like more than 99% of the coverage area. And about the satellite integration in 5G, when they were proposing the 5G at 5G plus, like 5.5G. So they were thinking about integrating the satellites in the network, but in 6G, they are also proposing that we will be integrating the satellites fully in the network. So you can find these stuff in the paper, which is like highlighted below, and we have shared the slides as well on the schedule. So how this is going to be happen, that they are providing the 100%, almost 100% coverage at every area of the world. So they are like the 6G motive is to connect anything, anywhere, and anytime. So how they are actually going to be happen. So they are integrating the satellites, the UAVs, the airplanes, the terrestrial network, and the internet of vehicles, healthcare, industry, urban area, rural area, and marine. So, like they are integrating every like thing which is on the internet or which is have the network. So how they are going to integrate those things. So there is a new type of architecture, which is an space air ground integrated network. So a space air ground integrated network basically composed of three segments. It has the ground network segment. Also, it has the air network segment and the space network segment. So this basically integrates these three types of consider these three types of network and integrate them to form a unified network architecture, which will be then providing the like the coverage area and providing services in the remote areas, etc. So I will be just briefly going through these ground networks. So the ground network is based on just that our cellular network and also the WiMAX and WLAN networks. And the air network consists of two sections. Like one is the high altitude, which will be composed of which is actually composed of the planes, and the low altitude, which is composed of the drones, or you can say the unmanned air vehicles. So based on the altitude, they have this air network is divided into two sections, and the space network. So space network, we have the satellite network. Also, the satellite network is divided into three I can say three categories based on their altitude from the Earth. So first is the geostationary like orbit, which like continuously revolves around the Earth with the speed of the Earth. And then there is a medium Earth orbit, and then there is a low Earth orbit, which is like closer to Earth and continuously moving, like completing their round around the Earth, maybe like in some hours. Actually, I have mentioned it in the next slides. So yeah, so these are some the difference between the satellites and some of their features. Like if we talk about the LEO, their altitude is like mentioned on the table. Also, the orbital period is like around 90 minutes to 120 minutes. Again, the MEO completes around 2 to 24 hours, and GEO is like continuously moving with the speed of Earth, so it continuously move around the Earth. So they have their own like round trip time and the data rate, and also which is the important thing is the computing. Satellite basically comes with the onboard computing. Onboard computing, so we can like utilize it for like providing some computation as well. So these are some application area of these LEO satellites. So question is, why satellites are needed if we are like already having the terrestrial network, like the ground network, and we are actually already providing the coverage almost everywhere. But still, there are some remote areas where we cannot deploy the infrastructure of the network. So we can use the satellite for the extending the coverage area, also providing some resilience. Like for example, if any disaster happens at that part of the Earth and the infrastructure actually got destroyed, like that portion is disconnected from the Earth. So how we gonna provide the rescue operations and the communication thing. So they can also provide these resilience at like this, providing the disaster management, and also provide the resilience, like a backup of if the like infrastructure destroyed, they can have a backup type of network. Also, it is like provide us mobility and network scalability. So the SAGIN, the Space Air Ground Integrated Network, has many applications, not limited to these, but it can have many applications as well. So like going from smart agriculture to every like type of application, it can be possible. So our focus is on the SDN enabled SAGIN network. The SAGIN network is already there. So people are actually trying to have this network as an SDN enable. So how they are making this network as an SDN enabled network? They are placing the controllers on each layer based on like decided based on some algorithms, some problem formulation. They are deciding that which of these network substrate can be the part of the SDN network. So this is basically just the SAGIN with the SDN enable network. Also, there is some another like type of network which we have that where we should place the SDN controller. So this is just the SDN enabled SAGIN network. So for the SDN enabled SAGIN network, we have these potential challenges, not limited to these, but there can be many challenges as well. But these are like the potential challenges, like deploying the controller that where we should place the SDN controller in this type of network. Also, because we have the mobility of control and data plane, like if we have deployed a controller over the satellite and it is already moved outside of the scope of the user. So how we will be managing this mobility of the control and the data plane. Also, that network topology is very dynamic in Sargent network because of the mobility. Exactly, like if you consider the LEO satellite, they are moving with a very high speed. Like in an area, they just like I mentioned in the previous slides, that it covers the completes its circle around the Earth in just 90 to 120 minutes. I think it was like that. So it will be that the network topology will be very dynamic. Like it will be changing with time, like quickly changing with the time. Also, we have the because of the multi-layer of the network, we have the slice and resource management problem as well. These are actually some potential challenges in this network. So just like I mentioned, that where we should place the controller in Sargent network. If we are considering placing the controller at geo satellite, it is okay. Then how the geo satellite will be managing the ground station and the LEO and the MEO area. If we are placing the controller at the ground station, then how it will be controlling the overall network. So like if we fix the controller on the any of the satellite, like for example, we fix the controller on the geo satellite, how we can how it can be helpful in managing the quality of service. So the like satellite is moving and it changes the position over the time. So how we can keep track of the user geographical position with respect to the variation in traffic, that if the traffic is variated and the controller is shifted to goes out of bound of that area of the user, then how user will be getting the data or user will be getting the service. And also what to decide, where to decide that on which layer where the controller should be placed. About the topology management, for example, this is a picture from another paper. I think I didn't mention the paper. Okay, so this is actually the an aircraft moving on the Earth, and they have this satellite. The aircraft is getting the service from the satellite as well as the ground station. When it comes in the vicinity of ground station, it got connected to the ground station and got the service from that ground station. But when it move in a remote area, just like if we consider like an ocean, so it will be like getting its service from the satellite. So the topology will be very dynamic. Then how we are going to manage this topology management. So these are just three main problems. One is the link failure, how the link failure will be tackled, and how the resources will be discovered with the dynamic topology. So in mobility management, there are actually two types of problem. First one is the control plane mobility, and the second one is the data plane mobility. In Sargent network, there is the problem of movement, like rapid movement. If we place a controller over the plane is also moving with a speed, and user is also moving with a speed, then how we can like forecast that from which plane or which area user should get the service. And for the control plane, obviously, that if that plane moves outside the coverage area of that user, then how the handover will be happen in the mobility management. So these are actually the potential challenges which we are actually looking into while considering our Sargent network. So about the network slicing and resource management, obviously we have different type of network and how to allocate the resources and how the slicing will be done. So we are looking into these direction. For this, we have an intent-based networking mechanism which actually translates the business intents into network policies and deploy over the infrastructure network. And then continuously monitoring done to assure that the intent or the service which actually user is requested or the policy is formed is like validated or not. So if it is a closed loop system, and this is basically a remake of the Cisco's intent-based networking picture. So there, the basic objective of this intent-based networking is the automation and network assurance, and then enhance security and optimize network performance. Obviously, from the continuous monitoring of the network, we have this. So in the direction of intent-based networking, we have already done these two projects. Not these two, we have actually done a lot, but these are two worth mentioning in this slide. So the first one is about the routing. So this we use the core network for providing the routing on the using the intent-based networking. So it was a project, and we use the intent-based networking for providing intelligent network automation by providing routing mechanism through intent-based networking. And the second one is also based on the core network. It involves actually several parties, like we have the Cambodia and Myren and TNCC. We have the TNCC network as well, and core network as well. And we have a collaboration with Pakistan, the PERN. So we deploy this quality QoS assurance intent-based mechanism over these network. We deploy actually an overlay network on this infrastructure network, the overlay network, and then we deploy the end-to-end clouds between them, between these network. So the question is how if IBN can be applied to this Sergeant network. So yes, it can be applied because we have to deploy. We have some, like this paper actually has an architecture that how this control architecture will be deploying over the Sergeant network. Like there is an intent-based networking, and it is also a closed loop. It will be providing the network policies or control commands over the network, and each layer has their own control interfaces, and control interfaces will be deploying the policies on the infrastructure, and then they have the monitoring as well, for making it a closed loop. Like monitoring will be providing the control to the integrated network control system as well, for the making it a closed loop architecture. Like it can be done. So if we consider our scenario, like we also have this kind of intent-based network, in which the business intent will be provided by an intent manager through a GUI interface. Like if you want to have a service for each of these layers, so these can be deployed through this intent-based networking architecture, and also it is also a closed loop architecture. The main important thing is the domain knowledge-based intent translation. The translation is important. That it can be a case that where a user actually the intent actually requires just the ground infrastructure and not the space or the air infrastructure. So we have a we will have a mechanism over here in our IBN, that it will translate the intent based on the domain knowledge, that what kind of domain that intent is required, and then it will make the policies accordingly. And the another thing is the important thing, which is the monitoring part, that how the intent is going to be assured. So for monitoring, we can use the Grafana and the Elastic ELK stack as well for monitoring the stuff. So considering about the special cases of Jeju Island. So Jeju is like the south part of the Korea, and it is a very beautiful island. I invite you all, if you have time, you can come and visit Jeju Island. So it is surrounded by the sea, like it is an island. So most of the portion of the south part of the Jeju is considered of this composed of the sea, and that's why actually companies are thinking about making a launch pad over there, because it is like if it got failed, then it can go down in the sea as well. So we had an space summit in Jeju Island, which was composed of like we invited the 50 space companies joined that summit, including the Momentous Space. You can read the names, like AWS was also joined that summit, and like they were like mentioning that Jeju is the most suitable place for deploying this launch pad. And currently, we are making the launch pad and launch vehicle for the Jeju Island, and they will establish a Korea Aerospace uh, uh, Research Institute for National Satellite Integration Operation Control Center on the Jeju Island for launching the small satellite like LEO satellites on the Jeju Island. Also, when the satellite number of satellites will grow in the network by the Jeju Island, we also need to manage the performance or analyze the performance of those satellites. So we also formed a KUA consortium. So it consists of SK Telecom, which is a Korean telecom company. Also with the collaboration of Korean Airport Corporation and Hanwha System, which will be in their commercialization in 2025. So this is all from my side. Thank you so much for listening and joining the session. Thank you so much, Professor, for allowing me.
I'm sorry. Now it is already the session time is much over. I'm sorry about that. Then we can end our session, our first session. Then our second session will start from 11 a.m. Thank you for your attending our working group session. Thank you. Thank you very much.